Yeah, welcome again. Today we're going to discuss the conservation of mechanical energy. So now let's consider that blue ball there. I hope you can see the ball. This ball is going to have some mass, obviously, and is on top of a tall place. It can be a building, it can be whatever. But what we know is that it is at a height above the ground. We just call the height h. Now, which type of energy does this ball have at this point? This ball will have gravitational potential energy, right? It has potential energy because it has rest. The ball is at rest, right? Now, potential energy must be due to something. In this case, this ball is in the Earth's gravitational field, so it has gravitational potential energy. So that's the energy it has there. This ball has no kinetic energy whatsoever because it's still not in motion yet. Now, if this ball should roll and fall to the ground, fall to the ground and hits the ground, then what's going to happen to the energy? The concept of conservation of mechanical energy only find its relevance if the body we are considering is in an isolated or a closed system. It has to be in an isolated or closed system before the mechanical energy will be conserved. Because in real terms, when this ball is falling to the ground, there will be earth resistance, friction, and all that. So the energy, the total energy it had in the initial starting point will not be the same energy to have when it hits the ground. Alright, it would have lost some of the energies to friction and all that. But if we are considering this body to be in an isolated system or a closed system where we can neglect the air resistance, friction, and whatever, so we're saying that no energy is going to be lost, no energy is going to be gained. This ball is just going to travel with all the energy it has, losing nothing, gaining nothing. Then we can begin to discuss. So, for conservation to work, the body must have to be in an isolated or closed system, or we assume that, right? We just neglect friction. So you see in some physics questions, they say neglecting air resistance, they say neglecting friction and all that. So you need to understand that we are neglecting all those things to define the conservation of mechanical energy. And also in real life, even though there might be friction and air resistance and all that, most times in some scenarios those friction and air resistance can also be neglected, right? It can be so small, infinitesimal, that we can neglect it, right? So it really makes sense. It's not just an isolated system. Something in real life, sometimes these things can also be neglected for real. So let's just see what we can do there. Now, this body has all kind potential energy here. The kinetic energy here is zero, simply because the body is not moving. Now, as soon as this body starts moving, it now has kinetic energy, right? But potential energy, anyway, let's just put the equations. Potential energy is defined as mgh. Now, in this body, I'll also do kinetic energy side by side. Kinetic energy is half mv squared. Now, what are the constants in this falling body? You see that this mass will remain the mass, so we can neglect the mass because the mass of the body is not going to be changing. Acceleration due to gravity is not going to be changing. What will be changing as this ball begins to fall is basically the height. So it's the height that will be the major factor, as it has to do with the potential energy. It's going to determine the magnitude of the potential energy. And in the kinetic part, the mass is going to be constant. So the velocity really is what's going to determine the kinetic energy. It means as the velocity is increasing, the kinetic energy is going to be increasing. And in this case, as the height is increasing, potential energy is going to be increasing. But the height is not going to be increasing, right? Because it's falling. So instead, I'm going to do it this way. As the height is decreasing, potential energy is decreasing. So as this body begins to fall, you see that what's happening to the height? The height keeps decreasing, decreasing, decreasing until it gets to this point. So at the very ground level there, no more height, so potential energy is zero. It makes sense, right? And at this point, potential energy is maximum. That means at the first point, because that's the highest level above the ground. So we know where potential energy is maximum. We know where potential energy is least, even equal to zero. We know where kinetic energy is least at the starting point where the no motion, so the kinetic energy is equal to zero. And then as this body begins to fall, what happens? It keeps accelerating. Remember, for a body falling, is accelerating, and thereby the speed or the velocity is increasing. So this kinetic energy will keep increasing until it gets to its maximum just as soon as it's about to hit the ground. So at this point, kinetic energy is maximum. That's what we are going to say, or that's what we're saying. So at this midpoint, every point in between this part, it does not have only potential or only kinetic energy. It is partly potential, partly kinetic. So all through the falling process, some of the energy is potential, some of the energy is kinetic. It is potential because of height, it is kinetic because of it has a velocity. But as soon as it hits the ground, no more height above the ground, potential energy is zero, kinetic energy is maximum. Now, from the conservation of mechanical energy, what we're saying is this: it doesn't matter the changes, the switching from one form of energy to another, because that's even the law of the conservation of mechanical energy, that this mechanical energy cannot be created or destroyed. So what we're saying is that all the total energy that the body started with, it started with potential energy, right? This is the initial energy. It must be equal to the sum of the energy it's landing with, which is kinetic energy. So that the potential energy, some of the potential energy must be equal to some of the kinetic energy. And this is because no other energy has been added to the system, none has been lost. So if we started with 120 joules of potential energy, it's also going to end with 120 joules of kinetic energy. Nothing lost, nothing gained. So this is the principle of conservation of mechanical energy. And then we can just derive an equation for the maximum velocity, because you know that if we are saying that potential energy is equal to kinetic energy, then look at the potential energy we are talking about. This maximum potential energy, the energy the body started falling by, and then this maximum kinetic energy. So we can have an equation there. Since we are saying potential energy is mgh, that it is equal to kinetic energy is half mv squared, where that v squared is the maximum velocity, because as this body keeps falling, the velocity keeps increasing until it reaches its maximum value there. So since the masses are the same, is the same ball falling, we can just cancel out the masses, and then we just make v the subject of the formula, and that will be it. So we multiply both sides by 2 to eliminate 2. You see that these 2 can now cancel these 2. So we just have v squared is equal to 2gh. And this is maximum, So finally, that the velocity, the maximum velocity, will be given by taking the square root of both sides. We have square root of 2gh. And that is it. Conservation of mechanical energy. Thank you for joining. Make sure you share this video if you really found value. Subscribe, like, drop a comment, and God bless you. Thank you.